Okay, today we're going to be looking at vector spaces and linear independence. If we begin by looking at vector spaces, a great place to start is by defining a vector. So a vector is an element of a set V, which we call a vector space. So a vector space now is a non-empty set equipped with an addition operation and a scalar multiplication operation such that for all values of alpha and beta, where alpha and beta are real numbers, and vectors u, v and w, which are all in this vector space, we have these two statements. So we have the vector u plus the vector v, and when we do that we still get a vector in this vector space v, and we get another rule which is alpha multiplied by the vector v will still be in this vector space. So a non-empty set, if you are wondering, just means the set contains at least one element. Now, going back to our two statements, these statements can be extended so that we get a bunch of other rules. So let's say we had the vector u plus the vector v. This is the same as doing the vector v plus the vector u. So this rule is called the cumulative law of addition. Another rule that we get is if we do the vector u added with the vector v plus w, that's the same as doing the vectors u plus v first, then adding w. So this is called the associative law for addition. Another rule is that there is a single member, 0, of the vector space v, and we call this the zero vector. You can see why this is true, because if we put any vector over here and alpha as 0, we get this 0 vector. Another rule is for every vector v in the vector space, there is an element or a vector w in the vector space called the negative of v. All that's saying is that if we had the vector v plus by the vector w, we'll get 0, because w is just equal to minus v. And again, you can see that is true, because if we had alpha is equal to minus 1, we get minus the vector v. Another rule that we can have is alpha multiplied by the vector u plus the vector v is going to be equal to alpha multiplied by the vector u plus alpha multiplied by the vector v. This is known as the distributive law. And following on from this, if we had alpha plus beta multiplied by v, this is equal to alpha v plus beta v, where v is a vector. And as this follows on, this is also known as a distributive law. If we now had alpha multiplied by beta and the vector v, this is the same as doing alpha multiplied by beta, then multiplying it with the vector v. This is known as the associative law for scalar multiplication. And finally, if we had 1 multiplied by the vector v, we just get the vector v. So the definition of a vector space is that it must follow that these statements are true. The vector u plus the vector v must still be in the vector space, and alpha multiplied by the vector v should still also be in that vector space. These rules can then be extended to get all of these rules. So all you realistically need to know is these two rules is what defines a vector space. Cool. Moving on to linear combinations. So suppose we had the vector v, which is equal to a1 multiplied by v1 plus a2 multiplied by v2 plus a3 multiplied by v3, all the way up to ak multiplied by vk. So the vector v is known as a linear combination of the vectors v1, v2, all the way up to vk, where with the scalars, which are a1, a2, all the way up to ak, being called the coefficients. We'll come back to this idea a bit later. This links heavily with linear independence. Okay, moving on. The definition of a subspace. So a subspace W of a vector space V is a non-empty subset of V that itself is a vector space under the same operations of addition and scalar multiplication as V. What this is saying is, let's say we had a vector space V. We can take some vectors away from this vector space and we could have a subset of W. This W is now a subspace if and only if it follows the two rules that we saw before. So if V is a vector space, then a non-empty subset W of V is a subspace if and only if for all the vectors U and V which are in this subset W follows the rule that when we do the vector U plus the vector V, this new vector is still in this subset W. So that's the first rule. And the second rule is for all vectors V, which is in the subset W, and alpha, which is a real number. If we do alpha multiplied by the vector V and it's within the subset W, we have a subspace. So if these conditions are true, that means W is a subspace of V. So if this is true and this is true, we have a subspace of V. So determine if subset U is a subspace of X, which is a real number. We have a subset where we have X, Y, given that Y is equal to 2X plus 1, and then X is all real numbers. So let's say we put X is equal to 1. That means we get the vector 1, and then we sub that 1 into here to find out what Y is. So 2 multiplied by 1, and then plus 1, which is 3. If we then sub in 2, we get X is equal to 2, and then to find out Y, we sub it into here. So we get 2 multiplied by 2, and then plus 1, which is 5. So we have these two vectors now, which are in this subset U. If we now see if these two vectors follow these rules, what we are first going to do is add the two vectors. So 1, 3 plus 2, 5, which gives us 3, 8. So if we look at this now, if we sub in this vector into here, we get 8 is equal to 2 multiplied by 3 plus 1, which clearly isn't true because 8 is not equal to 2 multiplied by 3 plus 1. We can clearly show that the set U is not a subspace of R as the addition operation is not met. Oh, okay. Now we have, if we first look at S1, we have S1 is equal to X squared and then 0, given that X is a real number. We need to show that if the sets are a subspace of R cubed, so real numbers in the third dimension or in 3 dimensions. To do this, let's say we have X is equal to T and then X is also equal to G. So now we get the general vector T squared 0 and then G squared 0. If we now add these together, we get T plus G, T squared plus G squared, and 0. So now if we say that T is equal to 1 and G is equal to 2, we get 1 plus 2, which is 3, and then 1 squared plus 2 squared, which is 5, and then 0. So looking back at this, we can see that X is equal to 3, If x is equal to 3, then x squared should be equal to 9, which is not the case here. So we can say that S1 is not a subspace of R cubed. So this is proof by counterexample, which is sufficient to prove that a subspace, so a subset, is not a subspace. If we now look at S2, we have doing the same thing. If we say x is equal to t and then x is equal to g, we have t 2t 0 and then g 2g 0. We're going to plus them together. So we have t plus g, 2t plus 2g, and then 0. So now we can say that we have t plus g, and then factorizing out the 2, we get 2t plus g, and then 0. So since t plus g is in the set of real numbers, as x is in the set of real numbers, we can say these two vectors, which I'll label as u and v, we can say that u and the vector v added together is in the set of S2. We now need to see if this is true on the scalar multiplication. So if we have alpha, which is a real number, and the vector x, 2x, 0, doing alpha, if we call this vector x, we get alpha x, 2x, 0, which we can write as alpha x, alpha, 2 alpha x, and then 0. And since alpha x will be in the set of real numbers, the vector x this time, subspace as squared. Now, we must also check that this is non-empty. So to check if this is non-empty, we take x is equal to 0, and we get 0 multiplied by 0, 2 multiplied by 0, and then 0. So then we get 0, 0, 0. So this contains... So now that we have shown that the addition operation works, the scalar multiplication operation works, and it is non-empty, we can clearly conclude that S2 is a subspace. Cool. Moving on. If we now look at linear independence, if we have the vectors v1, v2, and vk, which are a set of vectors in a vector space V, then the vector space equation is given by a1 v1 plus a2 v2 plus all the way up to ak vk, which is going to be equal to 0. So this is the vector space equation, and we always have a trivial solution where if a1, a2, all the way up to ak, so all of these coefficients are 0, this equation is met. So this would be our trivial solution where all the coefficients are equal to 0. If this happens to be the only solution for this vector equation, then we say the vectors v1, v2, all the way up to vk are linearly independent. So we're going to come back to this question and this one, and we're going to test if these vectors are linearly independent. So let's say we had vector 1, which was 1, 2, and vector 2, which is 3, 6. So now we get alpha 1, 1, 2 plus alpha 2, 3, 6 is equal to 0. So this gives us alpha plus 3 alpha 2, then 2 alpha 1 plus 6 alpha 2 is equal to 0. So then we get alpha 1 plus 3 alpha 2 is equal to 0, and then 2 alpha 1 plus 6 alpha 2 is equal to 0. What you can notice is that this, if we times this equation by 2, we get this equation. That means that there are an infinite number of solutions. Therefore, linearly dependent, as you can have so many solutions. If we had another pair of vectors, v1 is equal to 1, 2 again, but now we have v3, which is 2, 3. Doing the same thing, we have alpha 1, 1, 2, and alpha 3, we'll change it to 2, 3 is equal to 0. So we get alpha 1 plus 2 alpha 3, and then 2 alpha 1 plus 3 alpha 3 is equal to 0. So then alpha 1 plus 2 alpha 3 is equal to 0. 2 alpha 1 plus 3 alpha 3 is equal to 0. So now, the only values of alpha that satisfy this equation would be alpha 1 being equal to 0 and alpha 2 being equal to 0. Therefore, these two vectors are linearly independent. If we quickly go to this question, here we have 3 vectors and they have 2 dimensions. 3 vectors. If we are going to check linear dependence, we do the same thing. Alpha 1, 1, 2 plus alpha 2, 3, 6 plus alpha 3 minus 1, 4 is equal to 0. So here we get alpha 1 plus 3 alpha 2 minus alpha 3, and then 2 alpha 1 plus 6 alpha 2 plus 4 alpha 3 is equal to 0. So we get 2 solutions, which is alpha 1 plus 3 alpha 2 minus alpha 3 is equal to 0, and then 2 alpha 1 plus 6 alpha 2 plus 4 alpha 3 is equal to 0. So we only have 2 equations and 3 unknowns. That means that there's going to be an infinite number of solutions, because this is going to be some 3D plane and this is another 3D plane which might cross it like that. So let's say this is where they cross. All of these will be solutions to this system of equations. If we did have to solve this, we have free reign over one variable. So if we say alpha 3 is equal to 0, we get alpha 1 plus 3 alpha 2 is equal to 0, and then 2 alpha 1 plus 6 alpha 2 is equal to 0. And this is what we had before. So we have infinitely many solutions for this, as we saw in that little sketch. So what we can see is that if we have 2 dimensions, but then 3 vectors, we have infinitely many solutions, and so our vectors are linearly dependent. And this is the case when there is a difference in the dimensions of the vectors and the number of vectors. So let's say we had 3-dimensional vectors, so 3D, and we were given 4 vectors. That means these 4 vectors would be linearly dependent. Okay, if we come over here, so testing for linear independence in a higher level of dimension. So given that we have k vectors, so v1, v2 all the way to vk, which are all real and in some n dimension, the vector expression can be given as alpha 1 v1 plus alpha 2 v2 plus all the way up to alpha k to vk, which is equal to 0. So this is the same as writing ax is equal to 0, where A is the n times k matrix whose columns are the vectors v1, v2, vx, and x is the vector x is equal to alpha 1, alpha 2, alpha, all the way up to alpha k transposed. And the vectors are linearly independent if and only if the linear system ax is equal to 0, 0 has only one solution of x is equal to 0. Now, to explain this a bit better, we're going to go question number 3. So here we have 3-dimensional vectors. Putting them into our vector equation, we have alpha 1, 1, 2, 3 plus alpha 2, 2, 4, 6 plus alpha 3, 1, 0, 1, which is equal to 0. And from before, we can put this equation into the form of A, where A is a matrix, multiplied by x, which is a vector, and it's going to equal 0. So in order to do that, our vector A, which is an n times k matrix, would be 1, 2, 3, 2, 4, 6, 1, 0, 1. So these vectors, which are its columns, and then x, which is our coefficients, and this is equal to 0. So this is the vector matrix A multiplied by x and is equal to 0. Just to check that, of course we do row times the column, so we get alpha 1 plus 2, alpha 2 plus alpha 3, which you can see as alpha 1 multiplied by 1, alpha 2 multiplied by 2, and then alpha 3 multiplied by 1. And if you do that with all the rows, you will be able to see that we have just written the same thing in its matrix form. So now we're going to simplify the matrix A using row operations, and we're going to reduce it to echelon form. If you don't know what this is, check out the video on Gaussian elimination. So to reduce this to echelon form, we first look at the first entry, which is a 1, so we don't need to change anything. So 1, 2, 1. This is a leading one. We now need to make all the entries underneath the 1 into zeros. So 2 and 3 must turn into zeros. In order to do this, we do row 2 minus row 1, 2 lots of row 1, so we get 0, and then row 3 minus 3 lots of row 1, so here we get 0 again. So we have 0, 0, and then 4 minus 2 lots of row 1 is 0, and 6 minus 3 lots of row 1 is 0, and then 0 minus 2 lots of row 1 is minus 2, and 1 minus 3 lots of row 1 is minus 2. So now we have this matrix, and we ignore this first row, and we look at the next row, and the first entry in this next row, which is non-zero, is minus 2. So this minus 2 we need to turn into a 1. In order to do that, we do minus a half multiplied by row 2, so we get 1, 2, 1, 0, 0, 1, 0, 0, minus 2. And now we need to make this entry into a 0, so we get row 3 plus 2 lots of row 2, which gives us 0, 0, 0. So now we look at the rank of this matrix. So this is just how many rows are unique. And we can see that there are only 2 rows which are unique. This first row and then this row. Because if we times this first row by 0, we'd get the last column. Sorry, the last row, hence why it's not unique. So our rank is equal to 2, and our number of vectors is equal to 3. So we had 3 vectors. So as our rank is less than the number of vectors, these vectors are linearly dependent. So we have shown that these 3 vectors are linearly dependent. If we do the same thing with this question, so alpha 1, 1 minus 1, 2 plus alpha 2, 0, 3 minus 1 plus alpha 3, 2 minus 4, 5 is equal to 0. If we now do this just the same way that we did when we had vectors of 2 dimensions, we have alpha 1 plus 2 alpha 3 is equal to 0, minus alpha 1 plus 3 alpha 2 minus 4 alpha 3, and then 2 alpha 1 minus alpha 2 plus 5 alpha 3 is equal to 0. So we have these 3 equations and we have 3 variables. So we need to solve this to see what our solution is. If I first go about solving these 2 equations, we get 2 alpha 3 plus 3 alpha 2 minus 4 alpha 3 is equal to 0. So 3 alpha 2. So that's just me doing alpha 1 is equal to minus 2 alpha 3 and then subbing this into here. This gives us 3 alpha 2 minus 2 alpha 3 is equal to 0. Subbing this equation into this last one, we get minus 4 alpha 3 minus alpha 2 plus 5 alpha 3 is equal to 0. So this gives us minus alpha 2 plus alpha 3 is equal to 0. So now we need to solve these 2 equations, which is 3, which we can do by timesing this by 3. So we have 3 alpha 2 minus 2 alpha 3 is equal to 0, and then minus 3 alpha 2 plus 3 alpha 3 is equal to 0. Adding these 2 equations, we get alpha 3 is equal to 0, and then we will get alpha 2 is equal to 0, and lastly alpha 1. So work this out by subbing it into this equation, and then alpha 1, if we use this equation, will also be 0. So the only solution is where all of the coefficients are 0, so these vectors are linearly independent. If we now do this same question using the matrix echelon form method, we have the matrix 1, minus 1, 2, 0, 3, minus 1, 2, minus 4, 5. We then begin by reducing this matrix. This is already a leading one, so that's fine. We now need to make these entries into 0. In order to do that, we have row 2 plus row 1, and then row 3 minus 2 lots of row 1. That gives us 0, 0, and then 3 plus row 1 is just 3, and then minus 4 minus 4 add row 1 would be minus 2. Row 3 minus 2 lots of row 1 is just minus 1, and 5 minus 2 lots of row 1 would be 3. Now we ignore the first row and look at the second row. The first entry in the second row is 3, which is a non-zero, is 3. So we need to make this 3 into a 0, so we do 1/3 of row 2. That gives us 1 minus 2 over 3, and then 0 minus 1, 3. We need to make this minus 1 into a 0, so we do row 3 add row 2. That gives us 0, 0, and then 3 minus 2 over 3, which is 7 over 3. And finally, moving to the last row, the first non-zero entry is 7 over 3. We need to make that 1, so we do 3 over 7 times by row 3. So we get 1, 0, 2, 0, 1, minus 2 over 3, and then 0, 0, 1. So here we can see the rank of the matrix is 3, and the number of vectors we had was 3, hence they are linearly independent. So the same as what we got before. So if we have a quick look at what this says, the rank of a matrix is always k less than or equal to n. So over here we had k is equal to n, where n is the number of matrices. Over here we had k is equal to n. So over here we had them equal each other, or it can be less than. So here we had a less than option. So now, if we replace k with n, if we do that over here, if we replace these k's with n, so this n, that means that the maximum size of a linearly independent set of vectors in the nth dimension would be n. So we know that if you now had n plus 1 vectors, they would not be linearly independent. So here we have 2 dimensions, so n is 2, but we have 3 vectors, n plus 1 vectors. So we know that these vectors would never be linearly independent. Hopefully that makes a bit of sense. If we look at question number 6, so here we have 3 4-dimensional vectors. If we use our matrix method, we have 1, 0, 1, 2, 0, 1, minus 1, 3, and then 2, 1, 1, 7. If we now reduce this matrix, we will get 1, 0, 2, 0, 1, 1, 0, minus 1, minus 1, 0, 3, 3. So that's a leading 1, and that's just me making all of these columns a 0. If we now continue onwards, this is our next leading 1, and we need to make these entries 0. So then we get, so that's just me making minus 1 and 3 into 0. So this is our row echelon form. So if we now count the rank is 2. There's only 2 rows which are unique. And if we count the columns, or the number of vectors, we get 3. These aren't equal, so this would be linearly dependent. Okay, let's just have a quick run through. So we have vector spaces. To define a vector space, it must follow this addition operation and this scalar multiplication rule. These 2 rules give us all of these other rules. Linear combinations is just if we had a vector, we can make that vector by adding a bunch of other vectors in that same vector space. The definition of a subspace is that if we have a vector space, then we could have a subset from that vector space, and that subset becomes its own subspace if it follows the addition and scalar multiplication rule. So in order to prove that a subset is not a subspace, we can just use a counterexample. But to prove that a subset is a subspace, we need to prove the scalar multiplication rule, the addition rule, and check if the subset is not empty, as we did over here. So linear independence is when we have this vector equation and the scalars are all equal to 0, and that's the only solution to this vector equation. To test if vectors are linearly independent, we can use the echelon form of this matrix A, where this matrix A is formed by the vectors which are given. Or we could make a system of equations and solve those system of equations as we did for this example. And so testing for linear independence in high dimensions, it's much easier to use the echelon form of a matrix rather than solving a system of equations like this, as this is a much longer process. And finally, a cool trick to seeing if matrices are linearly independent. When we have our row echelon form, we simply look at the rank of that matrix and look at the number of vectors or columns that were given. If those are equal, then the vectors are linearly independent. If they are not equal, then the vectors are dependent. And another thing is that if the number of vectors is greater than dimensions, we have dependent vectors. So here we have number of vectors, which is 3, and they are in 2 dimensions. So these vectors were dependent. Cool. Hopefully that all made sense.